I am Amrita from Department of Electronics and Communication Engineering, and my Tech Talk topic for high speed communications is time interleaved ADCs in communication receivers. Introduction to time interleaved ADCs. Time interleaved ADCs combine multiple ADC channels to achieve higher sampling rates. They are essential in modern communication receivers requiring high bandwidth. This presentation explores their design, benefits, and challenges in communication systems. Overview of communication receivers. Communication receivers convert analog signals into digital data for processing. They operate across a wide frequency spectrum demanding high speed conversion. ADC performance directly impacts overall receiver sensitivity and accuracy. What are time interleaved ADCs? Time interleaved ADCs utilize multiple ADC cores sampling sequentially. Each ADC samples the input signal at staggered intervals. This technique effectively multiplies the overall sampling rate. Architecture of time interleaved ADCs. The architecture involves multiple parallel ADC channels with synchronized timing. Digital correction techniques are employed to mitigate mismatches. The system includes a clock distribution network for precise timing control. Benefits of using time interleaved ADCs. They enable very high sampling rates beyond individual ADC capabilities. Power consumption per conversion can be optimized. They improve system bandwidth and allow for faster data acquisition. Challenges in implementation. Mismatches among ADC channels cause distortion and spurious signals. Timing skew and gain mismatch are significant issues to address. Calibration and correction techniques are necessary for optimal performance. Mismatch types in TI ADCs. Gain mismatch occurs when ADC channels have different amplification factors. Offset mismatch refers to baseline level differences among channels. Time skew results from slight differences in sampling instance. Calibration techniques for mismatch compensation. Digital calibration algorithms adjust for gain and offset mismatches. Timing skew can be corrected through delay adjustments in the clock. Continuous calibration ensures stable performance over temperature and aging. Digital signal processing in TI ADCs. Digital correction algorithms are implemented post ADC conversion. They help restore signal fidelity by compensating for channel mismatches. DSP techniques are essential for maintaining linearity and dynamic range. Applications in communication receivers. TI ADCs are used in RF frontends to digitalize the high frequency signals. They enable direct sampling of wideband signals, reducing the need for down conversion. Their high speed capability improves receiver sensitivity and selectivity. So, TI ADCs are used in RF frontends and they are enable to the direct sampling of wideband signals. So, and their high speed capabilities improves the receiver's sensitivity. Impact on bandwidth and data rates. Time interleaved ADCs significantly increase the effective bandwidth. They facilitate high data rates essential for modern communication standards. The design must balance sampling speed with resolution and power. Power consumption considerations. Multiple ADC cores increase overall power but can be optimized through design. Power efficient architectures allow for longer device operation. Proper thermal management is necessary to maintain the performance. Design trade-offs in TI ADCs. Higher sampling rates may lead to increased noise and linearity challenges. Resolution often decreases as sampling speed increases. Engineers must carefully balance speed, resolution, power, and cost. Recent advances in TI ADC technology. Integration of advanced calibration algorithms improves accuracy. Use of novel semiconductor processes enhances speed and power efficiency. Development of multi-gigasample per second ADCs is ongoing. Future trends in communication receiver design. Increased integration of TI ADCs with digital processing unit is expected. Adaptive calibration will become more sophisticated to counteract mismatches. Emerging standards will demand even higher sampling rates and resolutions. Practical considerations for system designers. Careful layout and clock distribution are crucial for minimizing skew. Calibration routines should be integrated into the system operation. Testing and validation are vital for ensuring high performance. So, these are the practical considerations for system designers. So, as there should be the careful layout and the testing and validation are very important for ensuring the performance should be at higher level. Case study 5G receiver implementation. High speed TI ADCs enable direct sampling of 5G signals. Calibration techniques improve linearity for complex modulation schemes. System designers must optimize power and performance for practical deployment. Coming to the limitations and future challenges, mismatch correction becomes more complex at higher speeds. Power consumption remains a concern for portable devices. Continued innovation is needed to overcome the physical and technological barriers. Coming to the summary of key points. Time interleaved ADCs are vital for high speed communication applications. Mismatch and calibration are critical factors affecting system performance. Ongoing research aims to enhance speed, accuracy, and power efficiency. Coming to the conclusion and outlook, TI-ADCs offer a powerful solution for modern high bandwidth communication receivers. Advances in calibration and digital correction will further improve their capabilities. Future developments will continue to push the limits of high speed data conversion systems. Thank you.